Hey, welcome. Today we're finishing up our logarithm notes. I'm just going to talk a little bit about these graphs. If you are watching this video, you might want to pause here and go ahead and copy down the graphs. And then we're going to work a couple word problems out. Super easy stuff. But the big thing that you need to know with these graphs, and I'll leave this up here for a minute, is that exponential and logarithms are actually inverses of each other. So when you switch from x to y, um, or you're finding x to y, it's also the same thing as switching x and y with logarithms. So on the left is the exponential. Some key features to kind of distinguish is that there's the horizontal asymptote at y is equal to 0. You have the domain of all real numbers, the range from 0 to infinity. Um, if you take a look at the XY chart, negative 1, 0, 1, and then we'll take a look at the XY chart with the logarithms, it literally flips. Okay. Your horizontal asymptote then also becomes a vertical asymptote where x is equal to 0. Your domain and range flip as well. And that's pretty much that. Now, this is a very basic, very generic graph. On the exponential side, you see 2 to the x. Logarithm side, you see the inverse of if I transported that into an exponential of log base 2 to the x. So kind of take that for what it's worth, but that's mainly what you're going to see with the graphing part. Any questions at all? Leave it up there. For those of you that are in the video, you can fast forward to the next thing if you want, but this is pretty much all. Does anyone need more time? Okay. So with logarithms, there's not too many different types of word problems that you'll see. You'll need a calculator for the most part for them. If you take a look at the application, this is just the next two slides are actually just background to kind of set you up. Some of you have probably seen a lot of this in maybe physics class or some type of science, but logarithms usually are with decimals of sound. If you take a look at that decimals formula, 10 log of I to the IT, it tells you that I is intensity, I of t is the intensity threshold, and that we also know that I of t is 1 times 10 to the negative 12. This is usually used in Richter scale for decimal sounds, which calculates the magnitude of earthquakes. So if you take a look at the next slide here, we've also got this next formula. I'm going to write these formulas out whenever we actually do the problem so you can see it. And where E is our seismic energy in joules, and E of 0 is equal to 10 to the 4.4. That's the energy released by an earthquake. So let's go ahead and go into these first two application problems, and then we'll finish with the last. Calculate the approximate decibel associated with sound so loud it will cause instant perforation of the eardrums. It means it'll make your eardrums burst. Where I, the intensity, is 1 times 10 to the 4th. So I'm first going to start out with, I need to find decibels. So I'm going to use the decimal formula. The decimal formula. And in most cases, in problems that you'll see on your exam, how you'll know the formula is it will be given to you. You will not have to memorize this formula. Okay. Yes. And that's exactly what I'm going to write here to kind of start you off. So d is equal to 10 log I over I to the t is the formula that we're going to use. We have I is going to be 1 times 10 to the fourth. And then I of t in that last part where it was explaining, it said that I of t was 1 times 10 to the negative 12. So if I was to simplify this, you can plug it into your calculator like that. But if I was simplifying this, I'd make this 10 log of 1 times 10 to the 16th. Just because that negative 12 is on the bottom, you can move it up top. Since it's all 1 times 10 to the power, the negative 12, that comes from the actual equation, part of the equation. So if you look up here, it actually gives you I of t in the problem as 1 times 10 to the negative 12, just from the original. And once again, this is information that you will have. So going back to what we have here, you'll be able to plug that into your calculator. 10 log 1 times 10 to the 16th. And then you'll get your answer of 160. Now, in your calculator, the log base is always log base 10. If you don't see, I think we might have went over this before, but if you don't see a base, like in this example where it doesn't give you a base, automatically assume the base is 10, meaning that there's a tiny little 10 here. 10 is the only one that you will never really see written. Right. Moving to example number 9. This again deals with a lot of the information that was given before, so I'm going to write it out here. The energy released from an earthquake was approximately 1.12 times 10 to the 12th joules. Calculate the magnitude of the earthquake using the Richter scale. Magnitude in the previous sample was 2/3 log E over E of 0. And then in the previous, they also gave you E of 0. So we're going to write in the E, which is 1.12 times 10 to the 12th, and then 10 to the 4.4. Divided by 3. All right, so calculating this out, I'm not exactly sure how far they want us to go out. I'm just going to say that this is your magnitude. Your magnitude is going to be 5.099. And once again, the decimals from the previous example, the magnitude, those are not formulas that you're going to have to memorize. You will be given those. I just thought that it would be easier to do a little bit of background knowledge on where it's coming from on the other slides. Questions at all up through example 9? All right. Then the very last one here is application. This actually has nothing to do with the previous two. This is just another way in order to use logarithms. This is an orange, has an approximate hydrogen ion concentration of 10 to the negative 4.2. Calculate its pH. It gives you the formula pH, and H plus is the hydrogen ions. So it gives you that. So we're going to go ahead and plug that into our formula here as well. So yes, the previous two were just decibels and magnitude. This one is just pH, and this one, if you look, it gives you the formula inside of it. So like where the other two, I wanted to give you a little bit more background. pH, hopefully you guys all have seen before. It's just the acidity or basic level of a non-solid, which should be 4.2. So if you think about it, drinking water is supposed to be about a 7. It's a neutral. It goes from 0 to 14, actually, on a pH scale. I believe. Okay, I'm not a science teacher, but if I remember correctly, water usually is about 7. 4.2 kind of fits with an orange because that's more on the acidic side of things. Whereas if you were going from 7, anything greater than 7 would be on the basic side.